when it comes to carrying out a line integral, you can do it by direct line integration. You could also do it using Green's theorem. We'll be looking at the two methods. Now, there are advantages to using Green's theorem. It's usually much shorter, a lot less work, a lot less writing than direct line integration, right? Now, we're going to be looking at some examples of functions where you perform a line integral. We'll look at the two methods, right? And of course, they should give you the same answer. Remember, Green's theorem is not always shorter, but for most problems, it is. So it's usually a shorter method, right? Now, you will remember that we can carry out a line integral. For example, if you have your x and y axis and you say you're integrating a function of x and y along, say, the curve y equals x squared, right? From x equals 0 to x equals 1. Something like this. You have 1. This would also be 1 because this is y equals x squared. And here now, this function of x, y, it represents a vector field. For example, suppose it is x plus y dx plus x squared y dy. The horizontal component of the vector will be x plus y, and the vertical component of the vector would be the x squared y, right? So let's say you might have a vector field, and if you draw the vectors in the vector field, as you go out, the vectors get longer as x and y increase, all right? Or in this case, I haven't done the calculations for the vector field in detail, but I don't think they would have the same gradient. So the gradients might change depending on the position, but it's a vector field. The function itself will be a vector field. We have x alone or x alone dx, or x and y dx, or some number mixed up with some number dx plus, and then a similar situation with x and y dy. Right, that's a vector field which you can consider as a force. Then along the curve, what you're doing is finding the work that is done as that force moves an object along that curve. Alright? Remember, in mechanics, work is equal to force times distance. Alright? Distance along the path, or in the direction of the force. So that's what you're really finding. Right? Now, in some cases, you have your x and y axis. In some cases, you might have a closed field, a closed curve, I mean. In this case, you would label the integral as integral of c. You should put the c here to show it's a line integral along a curve. We've done some examples before, right? It's a line integral along a curve. If you have, for example, y equal x squared, going from here to here, and then you turn again and come back to here along, say, y equals x. Then what you have is an integral in a closed curve. And how you label it is this, right? This part shows that it's a closed, an enclosed area, completely enclosed. It could even be a triangle, a rectangle, whatever it is, as long as it's an enclosed shape, right? And this is showing that it is a line integral, all right? So what you're calculating is the amount of work that the vector field, which is the function, would do is moving the particle up here along the y equals x squared and then back here along y equals x. Alright? Now, when we do our example, that will make it clearer. Alright? Now, let us look at this example. I won't work it out completely here. Let's look at it from now. In our next video, we'll do a particular example using both, well, in our next video we'll do the example using direct line integration and then do it again using Green's theorem. But let's talk about Green's theorem for a while before we finish, and then we look at the example. So Green's theorem. Now let P and Q be two functions. Functions of x and y. P and Q are two functions of x and y. It could be that P is xy or xy squared or whatever it is, and it could be that Q is some other function, x cubed y squared plus y or plus x, whatever it is, right? It's P and Q. And these functions are finite and continuous, right? That are finite and continuous. No breaks. Nowhere is in the function where you're being forced to find being forced to divide by 0 or anything like that. So you have to skip over it, right? It's continuous, right? Along the boundary, which would be the curve itself. It's a boundary. If it's a closed curve, you have an inside boundary and an outside boundary. So it's along a boundary C of region R. So the enclosed region is what we call R. Now, if the first partial derivatives are finite and they are continuous within the region and on the boundary, what we have is a situation like this. You have your x and y axis, and you have some boundary, and you have the region R. Then what Green's theorem states is this: the double integral within the region R of delta P by delta Y minus delta Q by delta X dx dy is equal to negative integral around the enclosed boundary of P dx plus Q dy. Now, I like to write it this way because what is presented would be something like this. First, the integral of P dx plus Q dy is equal to negative the double integral along the region R of delta P by delta Y minus delta Q by delta X dx dy. Right? So whether you switch the right to left or left to right, this is Green's theorem, the statement of Green's theorem. Now, the thing is, performing the line integral is often difficult and time consuming, right? But Green's theorems, they provide a shortcut to the line integral. Now what it states is that a double integral over the region R, as we see here, this double integral over the region R, it can be transformed into a line integral, and the line integral can be transformed into a double integral. So we can transform the double integral to a line integral, the line integral to a double integral. Alright? Now, you have certain conditions that must be met for Green's theorem to be applicable. Right? So, for Green's theorem to work, the curve must. Alright, these are the conditions. One, it must be closed. The starting and finishing point must be the same. You cannot have a curve like this and apply Green's theorem. That cannot be. It must be completely closed. Alright? So you must join both ends so that it is closed. Two, it must be simple. It must be a simple curve. Right? It does not cross itself. So a curve like this is a non-simple curve. It crosses itself right here. That cannot work, alright? Can't work with Green's theorem. And three, it must be positively oriented. That means the direction is in an anti-clockwise direction. The direction it travels is such that the inside of the curve is on the left. It must go anti-clockwise. Here, this is negatively oriented. It must not be this. It must be positively oriented. That means it must be like this. Right? Positively oriented. It means that if you're walking along the curve, the inside of the curve would be on your left. See the top of your head, right? The inside is on your left, the outside is on your right. As you walk along the curve, going around this way. So those are the conditions that must be met for Green's theorem to work. Now, here, we're going to evaluate the integral around a closed loop of a curve of 2x plus y dx plus 3x minus 2y dy. We'll do that in the next video, where we'll do it A by direct line integration and B by Green's theorem. Now, if you get something like this in exam, you may be asked to do it by direct line integration or by Green's theorem or both, right? But probably you'll be only be asked to do it using Green's theorem. If it's a take-home a homework assignment, you might be asked to do it both ways, all right? Just to improve your skills in both methods, right? But I think in an exam, you'll be asked to use Green's theorem, right? All right, so I'll see you in the next video when we work this out.